Hello everyone, my name is Rui. Today I'm going to present our work, Mutual Information State Intrinsic Control. This is a joint work between Rui Zhao, Yang Gao, Peter Bill, Folk-Tresp, and Wei Xu. This work is about reinforcement learning. Reinforcement learning is about learning by interacting with the environment. This learning paradigm is very similar to how human learns. For example, a baby can learn to play toys or eat food by interacting with the environment. Our work is based on the self-consciousness concept in psychology, which means that the agent knows what constitutes itself. Based on this assumption, we propose a new intrinsic objective, which encourages the agent to have maximal control on the environment. We compare our method and the other state-of-the-art baselines, and our method shows superior performance. And for the first time, it enables the agent to complete the pick and place task without any task reward. We define the mutual information reward function as the MI between the agent state and the surrounding state. Agent state means the state of the agent, and the surrounding state means the state of the agent's surroundings. We can write the MI into the KR divergence form as the KR divergence between the joint probability of these two random variables and the product of two marginal distributions. And then we can further rewrite the KL divergence form into the downscale-Borodan form. And based on the downscale-Borodan form, we can derive a lower bound of the MI quantity. In the second part of the method, we derive a surrogate objective for effectively compute the MI reward in practice. During training the MI estimator, we use all the samples in the same trajectory. And during calculate the reward for each transition, we only use the adjacent state pairs as the input to the reward function. We can summarize the algorithm into the figure. The short name for our method is called music. First, the agent interacts with the environment and collect the samples in the replay buffer. And then based on the data in the replay buffer, we can train the MI estimator. And then we can train the agent's policy to maximize the intrinsic reward as the mutual information between the agent state and the surrounding state. And then we update the agent's policy using deep deterministic policy gradient or soft actor critique. Frequently, we update the MI estimator with a stochastic gradient descent. In general, our framework encourages the agent to learn to control its surroundings. Now let's see some learned behaviors without any supervision or task reward. In the first scenario, they are the robot car agent and the red ball. And with the intrinsic reward only, the agent learn to control the red ball. In the second scenario, when there are multiple objects involved, the agent car can learn to use one object to control another. For example, in this case, it learns to use the red ball to control the blue ball. In the third scenario, the robot arm can learn to push the object into random directions. In the last scenario, more surprisingly, the robot arm can learn to pick up the object from the table. And this is done only with the intrinsic reward. When there are task rewards involved, we can have 3 ways to combine the proposed MI objective and the task reward. The first variant is the fine-tuning. In fine-tuning, we first pre-train agent's policy with only the music reward, and then fine-tune the policy with the task reward. The second variant is prioritization. In this variant, we sample the experience from the replay buffer using a priority. And this priority is the MI quantity in our framework. This is very similar to a prioritized experience replay, which is use the TD arrow as the priority for sampling. The only difference is that we replace the TD arrow with the MI quantity in our framework. The third version is the intrinsic reward. In this version, we add the intrinsic reward on top of the task reward. This intrinsic reward can help the agent to explore states which has high mutual information with its own state. We also compare each variant to more advanced reinforcement baselines. For example, we compare the fine-tuning version with the die-in. We first pre-train agent's policy with the die-in reward, and then fine-tune the policy with the task reward. In the second row, we compare the intrinsic reward version with variational information maximizing exploration. This method 1 uses the information gain from a Bayesian dynamic model to encourage the agent to explore new dynamic transitions. In the third row, we compare or prioritize the sampling version with the TD arrow-based prioritized experience replay. In this slide, we compare our method music with die-in. The die-in objective is to maximize the MI between the state and the skill option. And the music objective is to maximize the MI between agent's state and the surrounding state. So from this video, we can see that on the left side, with the die-in reward alone, the agent cannot learn to control the object. So it cannot further learn to discover diverse skills. On the right side, we have music plus die-in. With the music objective, the agent can learn to control the object, and further with the die-in reward, it can learn to move the object into random locations, depends on the input skill option. We also did more extensive tasks and compared the performance between music and the empowerment and discern. And also we did some experiments in the transfer learning settings, and we also show the insight of reward distribution. So in the first figure, we can see that the MI objective of music converges faster than the MI objective of empowerment. In the second figure, we first pre-train the intrinsic objective function in the pick and place task, and directly deploy the learned reward function in the fetch push and the fetch select task. We can see that this transferred intrinsic reward still helps the agent to learn quickly to solve the downstream task. In the table, we compare the discern and with and without music. So the objective of discern is to maximize the mutual information between the current state and the goal state. We can see the performance improvement from third line to the first line. This performance improvement is due to that with music, the agent can first learn to control the current state, and then with discern objective, it can learn to move the current state to the goal state. In the last figure, we show how the intrinsic reward distribution during a trajectory. We can see that when the agent scraper and the object move quickly in the same direction, then we have very high mutual information. But this is different from the single reward shaping, such as the L2 norm between the gripper and the object. Because with this simple reward shaping, the agent cannot learn to control the object. It can only learn to move close to the object. There are some future research directions. The first one is that when the existing state separation is suboptimal, then we need more new method to automatically learn to divide and select the states. And with different combination of state pairs, the agent can learn different control skills. And this is also shown in this table. The second research direction is that we can use the learned skills for hierarchical reinforcement learning. First, we can learn different control behaviors, and then connect these control behaviors with the skill option Z via die-in, and then use the skill option as a high-level action space for the meta controller in the hierarchical reinforcement learning paradigm. And then the agent can complete more complex tasks, such as playing billiards or building Lego. To summarize, we propose mutual information state intrinsic control. Music encourages the agent to control its surroundings and help the agent to explore and learn new skills in the environment. And then we can use the learned skills or propose the intrinsic reward function to help the agent to quickly learn to solve downstream tasks when the task reward is available. Thank you for your attention. Let me know if you have any questions.